Alrighty, so for today we are going to be talking about kinetic energy. Okay, so the concept of kinetic energy is simple. It's just another form of energy that we've already been talking about. I know my face is a little blurry in these pictures. I want the camera to focus on the words, not so much on my face. So just pay attention to what's on the board. So what is kinetic energy? Kinetic energy is another form of energy that we've been talking about lately. Okay, it's still going to follow all the same basic rules, so we're just going to list those down so that we have them. Make sure this is going in your notes. You're going to be responsible for this. You're going to do a little worksheet on it, and we're going to keep going. All right, so it's still kinetic energy. So we're still going to use the symbol of E, except we're going to do it as E subscript K, or we're going to do KE. Either one of these is a perfectly acceptable symbol to write down when we're doing formulas in it. Okay? Kinetic energy is still a form of energy, so we're still going to be using the same basic units. Our units are still going to be joules. Same as we did for elastic potential energy, we did for gravitational potential energy, and we did for work. It's still going to hold true. Likewise, like we talked about with potential energy, if we do work, that's going to cause a change in the amount of kinetic energy that we have. So anytime we do any sort of work, it can make your kinetic energy go up, which makes sense. If I look at this marker right now, this marker has no kinetic energy. Why? Because it's not moving. We talked about what kinetic energy is earlier. But if I do work, like I make my arm go, now it's moving, now it has kinetic energy. Simple, straightforward. The definition, just to redefine it, just so we can say it again, kinetic energy is the energy of motion. So in order for us to talk about this, our object has to be moving. It has to be in motion. It has to be moving across space in some way, shape, or form. But all three of these points are going to hold true. Okay, so if we have an object and it's moving, what are going to be the measurable characteristics that it's going to have? Well, remember, we're talking about matter when we're talking about kinetic energy. So if we're talking about a piece of matter, what measurable characteristic do all pieces of matter have? You have to have mass. So mass is going to play a role in how much kinetic energy we actually have. Now, we're not going to use the whole word every single time we're going to write it down, so we're just going to use the abbreviation of a lowercase m. Cool. So we have a mass, and that mass is going to be moving. So the bigger something is, the more kinetic energy it can have. But remember, it has to be moving. If you have a tiny little bug and it's flying, and you have a blue whale and it's just laying there dead on a beach, the tiny little bug is going to have more kinetic energy because it's moving and the other thing's not moving. But if they're both moving the same way, obviously the more massive object is going to have more kinetic energy. So in this case, mass is going to have a direct relationship with kinetic energy. So mass has a direct relationship with your kinetic energy. What does that mean? Bigger you are, more kinetic energy you're going to have. Now, it's not going to be perfectly even, equal relationship. It just has a direct relationship. We're going to figure out exactly the mathematics of that in a minute or two. But if we have a mass and it has kinetic energy, we said that mass has to be moving. So if that mass has to be moving, what does that mean? What is the other measurable quality that that mass has to have in order for it to be moving? Well, we talked about this all year. The second an object is moving, it means it's going through space over a period of time. So if you have an object that covers a certain displacement, so we have velocity, an object moving across a displacement over a period of time. So that is going to play a role in our kinetic energy as well. So we're going to use the V to represent that. Now, this makes logical sense. If an object has to be moving in order for it to have kinetic energy, it has to have velocity. And what kind of relationship do we think velocity is going to have with kinetic energy? It's going to have a direct relationship. The faster you go, the more kinetic energy you're going to have. And so what do you get? You're going to get a direct relationship with kinetic energy. So velocity has a direct relationship with kinetic energy. Mass has a direct relationship with kinetic energy. But those relationships are not equal. Those relationships are going to be slightly different. One is going to tend to have more of an importance, more of an effect on the kinetic energy than another value would. Now, in order to get to the formula, we got to kind of figure out and think about which one's going to have a stronger relationship in this case. Okay, so we have to figure out now which one of these qualities is going to be the most important. Well, as it turns out, if we look at these things, okay, as it turns out, mass, while it does play a role in calculating the kinetic energy, it plays a much, much, much lower role in calculating that kinetic energy for a particular object. It's going to play a role, it's important, but the speed, since the whole thing we're talking about is the energy of motion, the quality which measures the motion is going to have a much, much, much more dramatic effect. Okay? And so when we figure out the formula for the kinetic energy of an object, we end up with a formula that looks like this. The kinetic energy is equal to 1/2 the mass times the velocity squared. This formula is in your reference table. Okay? It's located about halfway down the back of your reference table, and it's incredibly important that you know it along with the gravitational potential energy formula and the elastic potential energy formula, which we did last week. Now, if we look at this, we have to make sure that it actually works. What do we want? We want this to come out to joules. So how are we going to get this to come out to joules? Well, let's see. The unit that we're going to use for mass is going to be what? We're going to get kilograms. And the unit that we're going to use for velocity is going to be meters per second. Okay, so 1/2 kilogram, that's not going to change anything. But when we square this, what are we going to end up with? We're going to end up with kilograms times meters squared over seconds squared. How does that come out to equal joules? If it doesn't, then this formula is fluff and I made it up and I'm just throwing it at you. But we got to make sure that it actually works in a real sense. So let's see how that works. Remember, we had said that joules originally, the first time we talked about it, was we had talked about it with work. And we had said that work was newtons times meters, and that's how we got to the joule. So somehow we have to get this to be newtons times meters in order for it to work out. How are we going to get that? Well, if we look, a newton times a meter is a joule. So we need to get this to equal that. How are we going to get that? Well, a newton, if you remember way back when, is mass times acceleration. So that's going to be mass, which would be a kilogram, times acceleration, which would be a meter per second squared. And then that would take care of the newtons times a meter. How do we get that? Well, if you look there, it's not that hard to see. You got the kilograms. You got meters per second, and then you're going to multiply that by another meter. So if you were just to do a meter out here as if it was the numerator and get rid of that, kilograms times meters per second squared, so that's the newton times the meter, gives you the joules. So the formula is balanced, the formula works, the formula gives you what you want. Okay, so a couple of pitfalls that I see people make when they typically do this formula that I don't want you to fall into. When you're doing this 1/2 is attached to the m. This squared is attached to the v. This is very, very similar to when we did the elastic potential formula, and I said pay attention to that square being attached to the change in the spring displacement. This squared is attached to the velocity. You have to make sure that you are squaring that quality. This is not a parentheses around this whole thing and you're squaring the m as well. You're squaring the velocity. Make sure when you're working with this that you pay attention to that. When you're rearranging the formula, that you pay attention to that. So we're going to do one together now just so we see how it works. We'll do a second one where we can just kind of rearrange the equation to get a value for one of the other qualities. All right, so here is our first practice question. How much kinetic energy does a 0.146 kilogram baseball thrown at 44.7 meters per second have? So we're going to do what we do with any question. We're going to make ourselves a key. Now, this one's nice and easy. write down what we have, what we don't have. So we are looking for kinetic energy. We put that in as our unknown. We put down our mass of 0.146 kilograms. And we put down our velocity of 44.7 meters per second. We write down our formula, 1/2 mv squared. We plug in our values, 1/2 0.146 kilograms times 44.7 meters per second and square. Really important, big mistake that I see people do. They'll write down the formula, and then when they go to put the numbers down, either the half or the squared disappears. Don't do that. Don't throw away points. You wrote it down. It's right there in front of you. Just follow through. Other mistake I've been seeing a lot of kids make lately is make sure you're checking the key with what you write down here and what's in the question. I had several people on the last test that the question would say one thing and they'd either flip the number values or they'd leave something out in the mistake. Make sure everything matches. Once you're done doing a question, go back and check. Make sure everything that you wrote down in the equation, the key, and the problem all match. It's a silly little loss of points, but there's a couple people who always lose points for it. So you do this. You do the 1/2 in mass. You do your 44.7 in squared. You then multiply those two out together. I'll give everybody a second to put this together, and you should get an answer of 145.86 joules. Okay, like we usually do, we're going to keep our answer to the nearest hundredths place, and that would be your EK. Simple, easy, straightforward question. Okay, so now we're going to do a second one. Okay, so here's our question. What is the velocity of a 58 kilogram cheetah if its kinetic energy is 24,389 joules? So we make our key. There's your three values, your velocity, your mass, and your kinetic energy. We don't know our velocity, so that's what we're looking for. We have our mass of 58 kilograms and our kinetic energy of 24,389 joules. So we write down our formula. EK equals 1/2 mv squared. But this one's a little weird because we're not looking for the EK, we're looking for the V. So what do? We're going to rearrange our equation so we can get our V by ourselves, like we learned to do in math in like 7th grade. So the V right now is connected to the 1/2 m. So we're going to get rid of that. But whatever we do to one side, we've got to do to the other. And so we end up with EK over 1/2 m, which is good, except we're not done. Because right now we have V squared equals that. We don't want V squared, we want V. So how do we get rid of the squared? We're going to square root. That gets rid of that. But we have to do that to this side. And so we end up with V is equal to the square root of EK over 1/2 m. Now we can plug our values in. So the square root of 24,389 joules divided by 1/2 of the mass, which is 58 kilograms. Do your math, and you should end up with a velocity of pause me if you want to do the math. The final answer should come out to right around 29 meters per second. Okay, so that's how you would solve for velocity. We'll do one more where we solve for mass, and then I'll give you a worksheet where you get to do a couple of questions for practice. Okay, so here's our third practice question. A running back traveling at 9 meters per second has 4,050 joules of kinetic energy. What is his mass? So there's our key. I'm going to write down the values that we know. So in this case, we know our velocity. So we got 9.00 meters per second. He has 4,050 joules of kinetic energy. So that goes here. And we are looking for his mass. Okay, so we need to rearrange the formula one more time. So we write down our formula. over there. We need to rearrange this one. We need to get it so that we can get this mass by itself. Once again, we're going to move the v squared, in this case, to this side. Get rid of that. Do it over there. You end up with ek over v squared equals 1/2 m, which is good, but do we want 1/2 of m or do we want all of m? We want all of m. So how do we get rid of half? We do the reciprocal. Reciprocal of 1/2 would be 2. That gets rid of that. But whatever we do to one side, we got to do to the other side. And so we end up with 2 times all of this is equal to a mass. So we want to do what's inside the parentheses first, then we want to multiply by 2. So our EK is going to be 4,050 joules over our velocity squared, which would be 9 meters per second. We're going to square that, and then we're going to double that whole answer, and that'll give us our mass. And so obviously that's going to be 81, and you're going to do 4,050 divided by 81. You're going to double that, and you're going to end up with an answer of 100 kilograms equals your mass. So those are the 3 different ways in which we can work with this formula for now. Now we're going to work with it in a couple of different ways, and I'm going to give you a worksheet now attached to this video that I want you to complete for the rest of the period. Whatever you don't complete in class, finish for homework, and it's due tomorrow in class. All right? See everybody tomorrow. Bye, guys. Girls, everybody else.